Welcome back. We are going to check out now number 15. And in fact, this entire page is really about understanding the graphical representation of these hypothesis tests. So let's check it out. So a hypothesis test was conducted using a critical value of negative 2.33. The sample results were X bar equals 80 with a corresponding test value Z equals negative 1.50. And they've provided us their hypotheses. So we're going to just graphically look at the relationship between traditional method and p-value method. So we'll start here with traditional. All right, so we're going to identify the critical region and shade and label our alpha. All right, I'm going to do red here for that. So our critical value, negative 2.33, and it's a left tail test. That less than sign tells me left tail. So it makes sense the critical value is negative. So the critical region for a left tail test is on the left. And we don't necessarily need this information, but I'm reviewing a little bit. So that area is alpha. And it does say label alpha, so you could also just point to it. So that's our alpha area. All right, and then it says graph the values of mu naught, X bar, and the test value. All right, so our null hypothesis was mu equals 85. So our mu naught is 85. I'll just kind of make a note here. So that tells you your mu naught. And then in the study, X bar came out to be 80. So the way we know where X bar is we look at its test value. So the test value, negative 1.50. So a test value of negative 1.50 tells me that 80 is there. So an X bar of 80 corresponds to a Z test value, test statistic of negative 1.50. All right, and I can see then that my test value is not in the critical region, so it's in the non-critical region. And you can label that if you would like or not critical region. And when our test value is not in the critical region, we do not reject the null hypothesis. All right, you could even add here on your picture, it shows this on the roadmap, you only reject H0 if your test value makes it into the critical region. All right, so let's see how the p-value method looks. All right, so it still says graph mu naught, X bar, and the test value. So the mu naught, let me go back to my purple color here. Mu naught is 85. And then our test value, negative 1.50, told us that 80 is there. All right, so in the p-value method, for a left tail test, the area left of the test value is your p-value. So we shaded the p-value. All right, and then the size of the p-value compared to the alpha area. So I can see here my purple area is larger than my alpha area. So my p-value is greater than alpha. And that's good. That means that we would not reject H0. So the decision of the test always has to be the same regardless of method. And that's what we're trying to show you here. So when the p-value is bigger than alpha, it means your test value did not make it far to the left. All right, let's try another one here, a two-tail test. So my computer is being slow. All right. So now we have a hypothesis test conducted and the critical values were Z equals plus or minus 1.96 Sample results were X bar 15 with corresponding test value Z negative 2.50. All right, so we have our null and our alternative hypotheses. So just making a note there, that's two tail because it is a not equal to, so two tail test. And the null hypothesis is mu equals 18, so mu naught is 18. But I will start with my critical region. All right, so critical values plus or minus negative 1.96 or plus or minus 1.96. So critical value at a negative 1.96, critical value at a positive 1.96. So for a two-tail test, half of alpha is in the left tail and half of alpha is in the right tail. All right, so label area alpha. Well, half of it's there and half of it is there. So alpha over 2 on either side. All right, so let's take care of part 1. Part 2, graph mu naught, X bar, and the test value. All right, so mu naught is 18. And then we'll know where X bar is by looking at the test value. The test value was negative 2.50. So that's down here into that red area in the left tail. And that tells me that an X bar of 15 is there. So my test value made it into my critical region. That means it's very far away from the 18, in this case, very far to the left of it, which means we have enough information, enough evidence to reject that null hypothesis. So test value in critical region, we always reject the null. All right, and that means that our p-value should be small. So when the p-value is low, the null must go. So let's kind of confirm that now by drawing the p-value and comparing. All right, so with the p-value method, we label our mu naught, and then our test value, negative 2.50, told me that 15 is there. And that little bit of area there is half of the p-value. So just like alpha is split in half for a two-tail test, half of the p-value will be on the left in this case, and then the rest of it using symmetry, if that's negative 2.50, if we come over here to 2.50, the rest of the p-value is there. So this is the other half of your p-value. So this 2.50 is not called the test value. There's only one test value. This number has no name. I just call it the partner of the test value, just to call it something. And then we can visually see that the purple areas here, the p-value total is smaller than the red areas here, the alpha areas total. So I can see that my p-value is smaller than my alpha. And technically, anytime p-value less than or equal to alpha, we reject the null hypothesis. Okay, so that's just looking at some graphs. And then we'll end here with just a couple problems, just using the p-value method, but thinking about traditional method as well. All right, so number 17. Nationally, it has been reported that the proportion of successful operations for a certain procedure is 70%. For a study at a local hospital, a random sample of 150 of these operations were selected. It was found 14 were successful. Using a 5% significance level, test the claim that the local hospital's true proportion of successful operations is different from the national proportion. All right, so we always start with looking for the claim being tested. So we've got our claim. So the proportion P different would be not equal to, nationally was 70%, so 0.70. And our null hypothesis gets equality. All right, so symbol-wise then we've got our P naught. And then it was a random sample of 150 operations. So there's our N. And 114 of those, that's X, those were the number of successes. And then 5% is our significance level, so that's alpha. All right, and because we're dealing with a hypothesis test about a proportion, we always use the one proportion Z test. All right, and you can go to the calculator, run that test. Make sure for P naught, you enter that in decimal, and that you enter, make sure you get the order right, the X and the N in the right spots, and then check your P-value. It'll be 0.1088 or 10.88%. And for the P-value method, you compare that number to alpha. So I'm just going to write my alpha over here was 5%. Let's write PV there. So my P-value is greater than my alpha. So the P-value is not lower than alpha. P-value not low. Do not let the null go. So if we were to do the traditional method, we know if we're not rejecting the null, that means that our test statistic or our test value would not be in the critical region. All right, and when we fail to reject the null, it means there is not enough evidence to support that claim that the true proportion of successful operations at the local hospital is, and we're just rewriting the claim here, not enough evidence to support the claim that the proportion is different from the national proportion. Okay, so for proportions, the only test we have is one proportion Z, but when we do hypothesis testing of a population mean, we do have to be careful to determine if it's a Z or a T test. So let's take a look at number 18. So the mean throwing distance of a football for Marco, a high school freshman quarterback, is 40 yards. The team coach tells Marco to adjust his grip to get more distance. For 12 random throws with the new grip, Marco's mean distance was 42.6 yards with sample standard deviation 4 yards. Using a 5% significance level, test the claim that the new grip results in a mean throwing distance greater than 40 yards. All right, so let's get our claim. I didn't highlight mean there, but we're talking about mean, oops, not cross out, sorry. Mu, mean. All right, so now we're talking means. So our claim is that the mean throwing distance is greater than 40. So we have our null hypothesis with equal. So mu naught is the 40, and then N was 12 throws. And for the 12 throws, the mean, so the X bar, the mean for those 12 was 42.6. And then the 4, this is where we have to be careful here to check if that's S or sigma, and it says sample standard deviation. So that's S, which means that sigma is unknown. And that's why over here we end up doing a T test. All right, I'm saying it again, sigma, because sigma is unknown. All right, so pay close attention to which standard deviation they gave you for the sample or for the whole population. And then the alpha, again, 5%. So that's alpha. All right, then you can grab your calculators and run the test, and you can always just check that you get those values. 2.29% is a p-value. And we compare it to our alpha, 5%, and our 2.29% is smaller than 5%. And technically, if it was less than or equal to, we would still say p-value low, let the null go. All right, so that means if we were drawing a picture and we saw the critical region with the traditional method, if we're rejecting the null, it means that our test statistic made it into the critical region. And anytime we reject the null, there is evidence. So rejecting the null, we say there is evidence to support the claim. And this was about the mean throwing distance for Marco using the adjusted grip. And the claim was that it is a distance greater than 40 yards. So throwing distance for Marco using the adjusted grip is greater than 40 yards. All right, so that ends my chapter 8 exam practice. And any of the problems from chapter 8 that we didn't complete in class, the full examples, you can always go back now and do those. There's already videos made of those notes if you want to practice sort of more problems putting it all together. All right, hope you found that helpful.